Hello everyone, this is Vera. It's a long time haven't to see us, and today we would like to talking about the topic about the robot learning. So first, let off to recall. Firstly, so far we have been learning the supervised learning. What's the supervised learning? This means we give the dataset a label, and the goal is to learn a function to map the data and the data's label. For example, the classification, regression, object detection, segmentation, and captioning. And for example, you can see the future learning like this. We can use the autoencoders uh, to produce the input data and the data uh, mm, through the encoder got the features Z and through the decoder layer and then to reconstruct the input data. And we use the loss L2 loss function to compare the final results. Today we'd like to talk about the robot learning. So, what's the problem? The problem is where an agent performs action in the environment and receives reward. And the goal is to learn how to take the actions that maximize the reward. And there's some example about the robot learning. For example, you can to flip the clothes, and you can use the robot to help you to finish some housework. This field is a very fast growing field. You can see in the 2024, from 2024, many startups and many companies got a very large funding. And many people put money eyes on this area. And for example, the Toyota Research Institute and the Meta AI Research and Google Robotics and Imitation Research. This is the overall of today's topic, and we will focus about 7 questions. First, let us to focus on the problem formulation. This is the graph of the formulation. This means the human gave the goal of the agent, and the agent got the uh, uh, recent state and the word from the physical world, and then output the action and the physical world to continue give the reward from the last action and the state and the state after the action. This is an example about the cutting pole problem. The goal about this problem is to balance a pole on the top of a movable cart. The state is angle, speed, position, horizontal, uh, um, uh, uh, horizontal velocity. The action is a horizontal force applied to the art. The reward is 1 each time step if the pole is upright. This is an example of robot locomotion. The goal is to make the robot move forward, and the reward is 1 each time step upright and forward movement. This is an example of Atari games. The goal is to complete the game with the highest score, and the reward is the score increase and or decrease at each time step. This is example about the goal. The goal is to win the game, and the reward is the one last turn, one if you win, or one if you lost. And for example, text generation, and the goal is to predict the next word. And the reward is one if correction and zero otherwise. And the also example is a chatbot. The goal is to be a good companion, and the reward is come from the human evaluation. One if the statistics, the -1 if unspecific, the 0 is neutral. Another example is close voting route, and the reward is the human evaluation. One if the close is folded, 0 is otherwise. Okay, next part we'd like to talk about the robot perception. What is the robot perception? It's about the state, ST. It comes from the physical world. Making sense of the unstructured reward. There are many problem, for example, incompletely knowledge of the object and the things, and perfect action may lead to a failure, environment dynamic and other agents. And the sensor for the robotics is about understanding the interaction with the world through the multimodal senses. This is an example such as the two fish eyes cameras and the string and pressure sensors and the perception computers like this. This means we through the sentence to get the information from the real world. So, robot vision is embodied, activated, and environmentally situated. Well, we are very similar with the example of left. It's about 2D image detection. And you can see the example on the right. It's about the robot vision. And robot use the image input to control his next action. So we can say there are three points about the robot vision and the computer vision. The first one is about the embodied. Robots have the physical bodies and experience the world directly. Their actions are part of the dynamic with the world and have the immediate feedback on their own succession. Active robots are active perceivers. It knows why it wishes to sense and choose what to perceive, and determines how, when, and where to achieve their perception. And the last thing is about the situated. The robots are situated in the world. They do not deal with the abstract description, but with the here and now of the world directly influencing the behavior of system. This is the uh, perception action loop. You can see uh, like this. There's the loop about the perceptive and the action. Then what is the reinforcement learning? Reinforcement learning trains agents that interact with an environment and learn to maximize the reward, the goal. And the graph like this, uh, environment agent gives the action to the environment, and the environment feedback the state and reward to the agent. Then move to the next step. Agent gets the state and the reward from the environment and feedbacks the action to the environment. So, it's a little like why is the reinforcement different from the normal supervision learning? Supervision learning is about like this. Uh, we we input data set to the model and we use that function to calculate the output, and the model outputs the prediction to the data set, and we use the loss function to compare the output. But the reinforcement learning is different. The reward and the states transitioned may be very random, and the reward RT may not directly depend on action AT. And the another things is reinforcement learning is very cannot back prompt through the world. It cannot compute DRT or DAT directly. And what the agent experience depends on how it acts. This is a case study of playing RTL games. The goal is to complete the game with the highest score, and the reward is the score increase and decrease at each time step. We use the Q function to learning it. This a neural network with center, and the network input states about 4 times 84 times 84 stack of the last 4 frames. Of course, after the RGB to the grayscale conversion, downsampling, and cropping. And we calculate the Q values for all actions. And finally, we give the 4 actions at the last layer, step 1, 2, 3, 4. This is a case study of the playing games. This is the AlphaGo, came from the January 2016. This is it can beat the 80 times world caption ratio. And in the 2017 October AlphaGo Zero come world, it beat number 1 ranked KG, and in the 2028, in the 20, in the 2018, AlphaZero came from it generalized to other games. And in the 2019, Moon Zero, it come to the world and it can plan through learning models of the game. And the more complex city games such as the StarCraft I and the Dota 2. In robotics, there are another topic is about uh, locomotion uh, and the manipulation. So we can use the model-free reinforcement learning to solve the problem like this. We can learn from trial and errors and require extended interactions. There are some problems such as the safety concerns, limited interpretability. For example, what if things go wrong? And it's some different about human. Human maintain and intuitive models of the world, valid, applicable, and simple, efficient. Next topic, we will talk about the model-based planning, about the physical world. Learn a model of the world's state transition function P, and then use the planning through the model to make the decision. Model may not be accurate enough, and for example, we execute the first action, obtain the new state, re-optimize the action sequence using the gradient descent. The key is the GPU for the parallel sampling or gradient descent. The key question is what should be the form of the step T? It's like this. It's the architecture of pixel dynamics, deep version foresight. Well, we use this architecture to produce the RGB input and focus on the state and action specific area and then just to modify or transform the image which about the action area and the output to the new image. This means we compositing mask between the original input image and the action production a small image. This is a transparent object symbol. The other things we'd like to talk about is the key point dynamics. This means we don't need to uh, a detection of the object. We just do detection and control the key points to control the things. For example, we can to the trajectory of this one. We can move the object just to control the key point of it. And this is the particular dynamics. And this is another example. And also another example, we can push to all letters in there. This is a particular dynamics. There are one machine and the 50 different 15 heaters to control the different actions. For example, graphing, we can use we can use a we can let the robot to finish the graphing like this, and and pressing in the another ways. And we can use this machine to make the dumpling. Another topic I would like to continue talking is about imitation learning. Supervised learning from a demonstration data set and learning from the demonstrations like this. And this is the behavior clone. Um, you can see the training trajectory is black, and the pi theta expected trajectory is red, and we learn the behavior from the historic experience. The iterative collection of the expert dimension is like this. Expert provided feedback and training and then training data through the supervision learning and output the policy to the robot in environment and output the trajectory and to the feedback the loop like this. There's some difference between the reinforcement learning and the inverse reinforcement learning. Reinforcement learning is input environment and reward into the reinforcement model and output to the behavior. But inverse reinforcement learning is like this. It's got the feedback from the behavior and the environment and output to reward to this means the modify to the policy to help model achieve the best goal. This is the implicit behavior clone. There's another name is about energy model. It's like this. We try to find the argument the mix the minimize injury in the action. This means we just we just to choose the lowest injury cost in all the production actions. Another amazing policy is about the diffusion policy. This is the virtual motor policy learning through the action diffusion. The left one is the explicit policy. We learn all things through a function. The middle one is the implicit policy. We through the energy model to find the meanest engine cost policy. And the right one is about the diffusion policy. We try to find the lowest gradient field in the map and iterative the action and iterative the step and then to got the final action about the A. So what is a robotic foundation model? I think there's no explicit city representation of the state, transition functions, or policy that maps to action. For example, you can see the example in the left. It's imitation learning. We can see the four different diffusion learning. If four different learning. The first one is the diffusion learning. It is what we want. The model can to predict the actions through the different way and uh, its average. And the last one, third one, and the fourth one, it's not balanced. Sometimes it cannot work. For example, the BET model, and sometimes it is not balanced. For example, the LST model and IBC model. So, currently, foundational vision and language model, the output may not always be perfect. It will always generate something reasonable, and uh, synchronized action may not always be optimized. The generated trajectory always be beautiful and renewable, and the name is different. Sometimes it's the visual language action models and the large behavior models. And this is the robotics function models from the 2022 to 2024. And recently, the famous model is PI0. PI0 is first released in October 2024. It can do many things of the housework. For example, the clean clothes, fold clothes, and make the coffee like this. Uh, the PI0 by physical intelligence produce it like this. We use the cross embodiment dataset, and then we pre-train the dataset, and after that we post the training, and then we do the simple in the distribution task. For example, the zero shot and the complicated in distribution task. For example, specificize the post training to different tasks and the unseen tasks. And open source Pi0 came from the February 2025. The evaluation of the robot learning model is still a problem because real-world evaluation is very costly and noisy. We have a large enough budget such that we can still make progress. Uh, and announcing is about weak correlation between training loss and the real-world success rate. Training objective vs the task-specific metric or training via and the testing horizons. And what about the evaluate in simulation? Do we have the dataset such like the ImageNet in the embodied AI? Uh, sim to real-world gap is a problem. Efficient access the generation is also the problem. And another problem is about digitalization of the real world and the procedural generation of the realistic and the devices sees a correlation between the scene and the real world. So my definition of the real-world models is action-conditioned future prediction. Action-conditioned robot interaction data to give the feedback to the foundation policy and foundation world models, and the feedback is included between in the foundation policy and the foundation world models. And there are still have some problem about the foundation models. For example, it's a little hard to do the task about 3D, and how do we control the structure period, and how we can learn the physicals, how we can correct it the wrong signal from the real world. So currently foundation models are not targeted for embodied agents, and large language models can fill an embodied related task. Limited understanding of geometric, embodied, and physical interactions. Reinforcement learning from human feedback. For example, reinforcement, you can see the example like this. And adaptation and lifelong learning. How we adaptation to a new scenario and adapt to the human performance and self-improve. This means lifelong learning is also the goal we want to achieve. Every robotics work is a system work. System level consideration, the problem like this, delays computing, modules talking to others. So there are remaining some challenges like this, which we talk about above. In the future, we hope to develop foundation robotic models. It can help humans to do the more work. This is all the things about these courses. We have about learn the robot learning, problem formulation, and robot perception, reinforcement learning, and model learning, model-based planning, imitation learning, robotic foundation models, and we also talk about the remaining challenges. This is all the things about today. Thank you for the watching, and please let me know if you have any feedback. Thank you.